Good afternoon. Good afternoon, and welcome to the Concrete Institute of Australia. I'm John Nichols. It's my pleasure to be your host for this afternoon's webinar on NEXGen concrete reconstruction. The speakers are Brodie Chan and Diana Geaboc. Our first speaker is Brodie Chan. A few words about Brodie. Brodie is the head of asset strategy for the Port of Brisbane. He has extensive experience in renewal, life extension and management of civil and maritime infrastructure for private and public sector clients throughout Australia, New Zealand, Southeast Asia and the South Pacific region. This includes, most recently, as the Associate Director for Asset Advisory at ADG Engineers and the Manager Asset Services for the Port of Brisbane Proprietary Limited. Brodie graduated from the Griffith University in 2014 with a Bachelor of Civil Engineering and practices as a Registered Professional Engineer of Queensland, Chartered Professional Engineer and APEC Engineer. Brodie is also the current CAA Queensland State President. Ladies and gentlemen, please join me in extending a very warm welcome to Brodie Chan.
Thank you, John, for the introduction, and thanks to everyone for attending. Obviously really look forward to the opportunity to talk to you about our experiences in managing not only aging infrastructure, but infrastructure that's in one of the most aggressive exposure environments. So I'll take the opportunity to talk through some of the particular issues that we've faced in managing these types of environments, as well as how we've gone about trying to remediate them. There's one particular project and one asset that we'll try and focus on through this presentation. So it's a wharf asset. So a lot of the Fisherman Island quay line was built around 30 to 40 years ago, but most of it is suspended deck. So it's conventionally reinforced decks on steel piles. Given that it all supports container operations, we have these thickened sections of deck, which are the crane beams and support ship-to-shore cranes, as well as transition slabs and relieving slabs, just to compensate and to take from a fixed structure to the land side where it's capable of movement. For most of our assets, and as a lot of people would appreciate, maritime infrastructure is designed for a 50-year design life nominally, and that's consistent with what we try and achieve for our assets. One of the key differences is the intention for the Port of Brisbane to be here for the long term. So we recognise that over time this will deteriorate, but we want to prolong the life of these assets for as long as possible, noting that the operational implications could be far more significant than having to replace it. The wharf that I'll try and focus on in particular was designed for a range of loads that are fairly common in port environments, but fairly unique to ports as well. If you're familiar with bridges, you'd know the likes of T44 loads, SM1600. When it comes to the wharves, we're talking about 90-ton forklift axles, so far more significant than a theoretical 25-ton axle. And that's with the intention of picking up a fully loaded 40-foot container in a lot of cases. We also have a range of stacking loads that the wharf is capable of, but the most significant apart from that is the container cranes. So some of these cranes, as you can see in the background of that photo, can be up to about 1,200 tons. Some of them, as we push into larger vessels, these cranes also get bigger and bigger. So it's a fairly unique environment, but one that's also introduces a lot of challenges. So the wharf that we're looking at also has a range of features to try and accommodate for these oversized loads. Through a tighter pile spacing in some of these areas, we've nominated heavy vehicle crossovers, and that's to operationally control where we put loads as opposed to it just crossing anywhere, but knowing that at least by concentrating it, we have a point at which we can always inspect and we can always manage more effectively. So this wharf and the area that we'll focus on is the relieving slab. So located at the back side of the wharf, just above the rock revetment. It's a 7-metre wide section of slab, nominally 600 mm thick, and it's conventionally reinforced, so single layer of reinforcement on the bottom. It's also constructed in segments, so being cast in situ back in the 1980s, that was the easiest method for construction, and it's seated on one side on the piled headstock. On the other side, it's on an unpiled abutment. So none of it's anchored in, and that's to enable it to move. So given that the port's largely built on reclaimed land, we expect in the order of 250 to 300 millimetres of settlement over 15 to 20 years. So just by compensating for this, it just enables us to make sure that we have the infrastructure that's built for the future. We just take the opportunity to touch on our approach to managing assets. So the port since 1996 has taken a very proactive approach, which was largely built around recognizing that there's a range of deterioration mechanisms. We want infrastructure to last. So what can we do to make sure that that happens? And so that was prompted by the construction of Wharf 6 and 7, primarily in around 1996. So from that point, in addition to the number of additional treatments and features that were included into new infrastructure builds, we started implementing routine visual inspections annually. So that would be through our maintenance contractors. And it's particularly with the intent of identifying any defects that may present as an issue in the short term to medium term. So not necessarily a long-term remediation approach, but if there is localized concrete spalling or localized defects that need to be addressed to make sure that it achieves that intended service life. From that, the second layer is the condition assessments. So over a 5-year horizon, we undertake detailed assessments for all of our wharf structures. And so that includes testing of reinforced concrete elements. We recognise that chloride-induced corrosion initiation is one of the largest risks that presents to our assets. So we do a range of test methods, which might be chloride content analysis, predictive deterioration modelling, half-cell potential surveys, cover meter surveys, and the like, to really inform on when we think that corrosion is expected to occur and when chlorides will penetrate to the depth of the reinforcement and be at sufficient concentrations to initiate corrosion. This ultimately feeds into our asset management processes. We produce asset management plans as part of this, which document our approach to managing the assets over the long term, the strategies that we apply to them, and the expected costs that are required to sustain the asset performance over the long term. As I mentioned, the condition assessments really target identifying when corrosion is expected to initiate. And at that point, we continue to track up until the point of corrosion initiation and implement a just-in-time intervention method. So as you can see in that photo, it just gives you a bit of a glimpse of a couple of things. Firstly, impress current cathodic protection is the primary means for us to try and remediate these assets and extend the life. So at the time for which corrosion initiates, we traditionally try and install cathodic protection. The other that it also shows, you can see personnel working in quite a constrained environment, working in and over water, as well as having to use quite significant means of removing concrete, breaking out and reinstating. Ultimately, a very challenging environment when you consider the tidal range that you have to operate in, the weather conditions and the exposure. So in 2019, we undertook a detailed condition assessment, which identified that areas of delamination were occurring on the soffit of the relieving slabs. Now, this was particularly concentrated towards the midspan, and you'd see that there's large areas in which exposed reinforcement on the bottom layer were identified. Severe corrosion, obviously, which prompted the concern. As well as this, you can see how the delamination seems to taper towards the edges on the outer periphery. Now, in some cases, we're also exposing both longitudinal and transverse bars. So this is really where we're talking about. You can see the relieving slab as a whole, as well as the area in the zone in which we're seeing the worst case of delamination, particularly concentrated towards that middle span or the midspan of the slab. Outside of that, no apparent signs of deterioration identified. from the image on the right, you can see from that survey the extent to which we're seeing defects identified. And as I've noted there, accounted for about 5 to 10% of the total deck soffit area just from that delamination survey, which is fairly significant in the context. One of the points I'll come back to later on, if you recall, is just where we have heavy vehicle crossovers, and we'll touch on that a bit further on. So if we're seeing it on one relieving slab, are we seeing it on others? Well, that is what started to become apparent in some of the other areas, particularly further down or downstream. As I mentioned, the Fisherman Island Quay line was started being constructed in about 40 years ago, and we've built further and further out to match the reclamation activities. So the newer wharves, once they started hitting a certain point, we started seeing issues. So further up the quay line on Wharf 5, this is one of the areas of delamination that we identified from a survey. From taking a core sample within that area over a reinforcing bar, you can see that corrosion's initiated in that zone. So ultimately a bit of a concern to us. And it prompts the question, where do we go wrong? Ultimately, we've talked about quite a proactive approach to trying to identify where deterioration's occurred, track the time towards corrosion initiation, and ultimately remediate it when we need to. With all this in place, we raise a few questions. So the first thing we did was take a step back and look at what's happened historically. We've implemented such a rigorous regime. Surely there's been something. So all through that 2008 period to right up to 2017, there were no signs of deterioration identified at all. It's worth noting that in the photo on the left, you can see that there's this apparent white coating that was applied. So that's an acrylic-based coating that was applied in the late 90s, early 2000s, with the intention of providing greater durability to the soffit of the slab. So acknowledging that it is a severe environment, the port tried to take a bit more of a proactive approach. However, it delaminated soon after it was applied, so it wasn't providing much benefit. Some of the other findings throughout the years were through the predictive modelling and testing campaign, in which it was expected that corrosion would occur or initiate in uncracked sections at some point in the future, 10 to 15 years in the future. But as you note, that's corrosion initiation as opposed to damage propagation. So all the way up until 2019, when we've taken a big step change and seen it propagate from just being potential corrosion initiation to quite severe delamination. The other key finding, as you see in the photo on the right, is in the apparently sound areas. So where there's no delamination present, the reinforcement was sound. So no corrosion to the reinforcement. So putting our engineering hat on, we've stepped through this in a methodical way, looking at both the durability and structural mechanisms for causing this deterioration. So we started with structural assessment and looking at initially, was the structure designed for the intended loads? So a 90-ton forklift axle in the internal spans or edge spans. So whilst it was towards the limit of ultimate capacity, it didn't exceed the capacity. Now, I've just indicatively put up some of the assessment for where we do have steel loss, just to provide an indication of how significant this could be to the structure in terms of its capacity if we started to see more and more section loss, particularly in these high areas of peak bending. So in theory, it's designed for its intended loads. What we did find on a review of the serviceability limit state was that under that 90-ton forklift axle, we're seeing quite significant cracks. And when you compare to the likes of what would be stipulated through conventional transport and main road standards, and where anything over 0.3 millimeters and above needs to be remediated, we're already at that threshold just under serviceability. So up to 0.31 millimeter cracks expected at the edge span, so right at the edge of the joint. Again, ultimately, the structure is designed for serviceability, but we're inducing quite significant cracks under conventional loads. So what do we know? Well, as I pointed out, the structure was designed for the intended loads. One of the key points that I highlighted earlier was that we do have heavy vehicle crossover points. So for any of these oversized, overmass loads, they do go through 3 controlled areas, transitioning from the wharf to the land side. So given that we're seeing such widespread deterioration, it would point to the fact that, well, it can't be something that's just concentrated to an overloading event. It's highly utilized, but that's obviously more concentrated towards the edge span where it has nowhere to redistribute the stresses to. From a design loading perspective, again, whilst it's designed for serviceability and ultimate limit states and can take the loads, we're inducing crack widths of up to 0.31 millimeters. And it's predominantly in this zone of peak bending, so in the midspan, which would coincide with where we're seeing areas of deterioration. As you see, we've got a delaminated coating that's been applied, and that does add to the complexity of trying to inspect these structures over time. So probably a point to just remember for later on. So going through the various deterioration methods and the mechanisms, from a structural perspective, as I say, we would not expect it to be overloading, given that it's far too extensive and it's occurring across the extent of the slab. We have a range of controls that are implemented, and as the port, we do have other means of making sure that this does happen, including through our permitting processes. The slab itself, well, movement and articulation shouldn't be an issue. So we do have expansion joints throughout the slab that should accommodate for those stresses that can build up through thermal expansion and contraction. And as well, it's not in the plane in which we'd expect for it to be related to this kind of deterioration mechanism. So a lot of that cracking that we're seeing and the deterioration just doesn't coincide. So not movement and articulation. As you recall, the abutments aren't piled, so there is the potential for these slabs to be moved, but it is intended to accommodate for this movement. There's elastomeric bearing pads on either side of that relieving slab. So given that it is intended to be simply supported, it should be able to take that settlement. From a design loading perspective, we did find that obviously it's able to accommodate for the loading under an ultimate limit state. Serviceability, however, raises a few more questions. So it does point to this design load conditions. The next step was to look at the durability assessment. Now, as I mentioned, we do undertake quite significant testing over a range of horizons with the intention of understanding the point at which corrosion will initiate. So the graph on the left side is just the sampling for chloride ion content, for which we've taken the various depth increments from samples extracted from the structure over time and projected this out to the depth of the reinforcement, or the conventional depth of reinforcement. That red line is the industry accepted initiation threshold for corrosion. So as you can see, a lot of these uncracked and undelaminated zones were trending towards being below that initiation threshold. In the delaminated zones, however, they were tracking above the expected initiation threshold. From the half cell potential surveys that we took across delaminated or a delaminated and undelaminated zone, you can see that there are areas of high or more negative potentials, which present higher risks of active corrosion occurring in these delaminated zones, which is not unexpected. In apparently sound areas, there was much higher or more electropositive potentials. So I would suggest that, well, all these areas that are outside of the immediate zones of delamination aren't affected at all. We also undertook a range of test methods to investigate the likes of carbonation, which was well below the cover depths, so in the order of 5 to 10 millimeters maximum, relative to 65 to 75 mil of typical cover depth. Sulfide ion content was well below the industry accepted thresholds to present concern to corrosion. And as I mentioned, the key issues that we've always tracked in relation to chloride ion content, well, it was sound in apparently sound concrete and well below the threshold. in those cracked zones and delaminated zones, as I've just tried to highlight through that illustration on the right, was significantly higher and largely above the threshold. So where does this leave us? As I say, carbonation not of concern from our test methods, and this is the same for sulfate ion content. Alkali silica reaction is potential and known in the Brisbane River, and particularly given the age of the structure and use of reactive aggregates at the time, there is the opportunity, but also worth noting that given the defects were concentrated towards the midspan, very unlikely that it is ASR because it doesn't happen this way. Chloride ion content, again, apparently sound in areas that are or below the threshold in apparently sound areas. Those areas that were in zones of delamination and exhibiting cracking were found to have chloride ion contents at a level that were sufficient to initiate corrosion at the reinforcement. So it leaves us with two key areas that we're concerned about. And it really points to the fact that we've had the primary mechanism being the serviceability loading conditions that were inducing cracking on the soffit of the slab at that midspan, with a secondary effect. So it's provided a path of least resistance through to the depth of the reinforcement for chlorides to penetrate over time. The question that we move to is, well, how do we rectify this, knowing all of that? Obviously, the easiest way that everyone thinks is just to repair it. So if you've got everything outside of that zone being sound, well, surely we can just remediate and do a localized repair. But the reality is that this doesn't add to the capacity of the structure from a serviceability perspective. We're still inducing potential cracking under the conventional loading conditions. So over time, we're going to suffer the same fate. So at best, all we're doing is just reinstating it to its as-built capacity, as opposed to trying to increase the capacity in these high utilization zones. So in situ repairs were not necessarily the preferred and not necessarily viable either. So ruled out a range of potential remediation methods, which left replacement as being one of the preferred options. As part of this, there were a range of methods that were considered. So demolition of the existing slab was consistent across all these methods, but what really varied was how we reinstate the existing slab. Cast in situ, again, very viable. One of the key operational risks is that you take out the slab for a long period of time, have to reinstate all of it on site, takes longer, takes the key line out for a longer period of time, ultimately a greater operational impost. Precast and conventionally reinforced slabs, another viable option. So all of this gets cast off site in controlled conditions, bring it to site, we land the slabs. So a much quicker turnaround time, slightly higher cost, but ultimately achieves a very finished and quality product at the end of the day. The other option is the replacement with precast slabs, but instead of conventionally reinforced, it's pre-stressed. So potentially creates thinner slabs, but as well has the trade-off. So particularly in a marine environment, it's not the preferred approach given the potential risk of catastrophic failure. So what did we learn through this process? Well, we did raise some questions about what is an acceptable crack width, and I think it's a question that is asked throughout the industry. Whilst there are standards that take a view on this, particularly in a marine environment, it probably opens up more questions than it answers. As you've seen, under serviceability loads or under serviceability limit state loading conditions, we're seeing crack widths expected of up to 0.3 millimeters, which isn't out of the realms of what the industry expects as standard. So probably points more to the fact of undertaking that durability assessment during design and evaluating what is acceptable. One of the other key learnings for us was the loading conditions and what we designed for. As you've seen, the forklift, which induces 90-ton front axle loads, induced quite significant crack widths. Now, under conventional logic, the serviceability limit states don't apply for these type of extreme loads. But as you say, this is the day in, day out type of operation that we have at the Port of Brisbane. So really, whilst it wouldn't have been a consideration, or this loading condition wouldn't have been of consideration for the serviceability limit state design, it probably should have been. The inspection and testing regime, whilst it didn't point us to the fact that there was deterioration or alert us to it, it's always a continuous learning process for us at the port. So we've taken this into consideration to make sure we adapt our regime to identify these potential issues before they arise. And the application of that acrylic-based coating system is one that we take away. Again, everyone thinks that more is better than less, particularly when it comes to durability, it's belt and braces. But what we did find was that it concealed the slab. So we'd seen cracking induced under conventional design loadings, but we're starting to see deterioration occur, and it's been concealed, and we haven't been able to identify it until it's too late. So again, points to the fact that making sure that if we do apply any durability treatment, that it's well conceived, consider trial applications, and make sure that it is applied by a suitably qualified applicator. So thank you very much. If you have any questions, look forward to answering them at the end.
And thanks, Brodie. I'll just take remote control back from you. Great, got that. And ladies and gentlemen, I ask you to join with me in thanking Brodie for a very interesting presentation. Our next speaker is Diana Geaboc. And a few words about Diana. Diana is a project manager for the Port of Brisbane. In this role, she is involved in delivering a variety of sustaining capital remediation projects, predominantly across the Port of Brisbane maritime assets. With a particular interest in solving durability challenges in the marine environment, Diana seeks to explore innovative ways of achieving project outcomes through the lens of sustainability, including optimising construction methodologies, recycling of construction waste, and using sustainable materials such as low-carbon concrete. Diana is also a member of the CIA NEXGen and CIA Queensland committees. Ladies and gentlemen, please join me in extending a very warm welcome to Diana Geaboc.
Thank you, John. Excellent introduction, and thank you, Brodie, for your fantastic presentation. As John mentioned, my name is Diana. I'm a project manager for Port of Brisbane. And today, following on from Brodie's presentation, I'll be discussing the delivery of two recent and related projects, the Wharf 1 and 2 relieving slab, which Brodie discussed in detail, and the Wharf 5 extension relieving slab, which was delivered also very recently. Brodie provided an excellent background and introduction to the whys behind the Wharf 1 and 2 relieving slab reconstruction. I'll be taking you through the methodology and how it was actually done. I'll be introducing some of the challenges that we faced during construction, and similarly, I will be discussing the Wharf 5 extension relieving slab, providing a little bit of introduction, as well as comparing the construction methodologies with what was done in Wharf 1 and 2. So the Wharf 1 and 2 relieving slab is 330 metres long. As you can see, this basically spans half of the operational terminal in which it was located. This is one of the key drivers behind the methodology that was chosen, as we knew this project was going to be a significant operational disruption for the terminal. The terminal operators are actually Port of Brisbane customers, so for us it's extremely important to keep these disruptions as minimal as possible for customers' sake and also our sake. As Brodie mentioned, 3 replacement options were explored: demolish and reconstruct in situ, demolish and reconstruct with normally reinforced precast panels, or demolish and reconstruct with pre-stressed precast panels. There are pros and cons to each option. At a high level, here's what we considered to be important when we were considering the construction methodology. Reconstructing the slab in situ while potentially offering a slight cost saving had a very long construction period. As I mentioned before, operational disruptions had to be minimized, so that ended up being ruled out quite quickly. Between the two precast options, we were looking at slightly higher prices, not so much from materials, but transport and handling, trucks needing to bring the panels on site, cranes needing to move them around, all of that. The benefit, however, of the precast solution is, slightly more visibility and control over the quality of the outcome. So it is much easier to QA concrete when it's made off-site. Each panel can be closely inspected, and ultimately it leads to a more uniform outcomes in terms of quality across the entire length of the project. Pre-stressing for us, which Brodie mentioned, it introduced a level of risks that we were unwilling to take. Considering the harsh marine environment, the benefits of pre-stress for us pretty much outweigh the risks. So, sorry, skipped a slide there. No surprise, we ended up choosing replacing with precast panels, normally reinforced concrete. The shorter construction time frame that was offered by this solution was just something that it was too appealing for us to refuse. So after a competitive tendering process, preferred contractors were awarded the contract and soon construction commenced. Pensar were the contractors that were successful and were awarded the work. One of the biggest benefits from this construction methodology was the fact that these panels were fabricated off-site, and essentially work could begin on demolition on-site while this was happening. In an in-situ type concrete construction project, we would have had to wait for the demolition to be complete, all of the prep work to be done, and then we begin forming up the slab and constructing it. So as you can see, we saved a lot of time having these activities happen in parallel. The previous slab was cut into pieces and lifted off by crane, placed onto the back of trucks and disposed off-site. What you could see on the right there is after all of that demolition had happened, access platforms were installed using scaffolding, the adjacent concrete was expected, and the bearing shelf for the new slab was being prepped. Sorry. As you can imagine, working over water is always going to be a challenge. So, oh, sorry, I keep skipping. Yeah. As you can imagine, working over water is going to be a significant challenge for us. This picture on the right really shows how far up the water comes on a very high tide, and this obviously brought about additional considerations of how we were going to access the areas that we needed to access when we were prepping the bearing shelves, checking all the angles and the adjacent structures. It's kind of difficult to do. You can't exactly float a boat in the middle of that work site. So this photo also really demonstrates well how the location of the slab was right in the middle of an operational terminal. The vessel that you can see behind there is a car carrier. So really we were very, very limited in the space that we had and had to work in with operations to ensure that their disruption was minimized, but also we had to keep the site very compact and basically needed to be in and out of there as quickly as possible. So the precast panels were all of the same design dimensions. I believe there were over 100 panels used in total. One of the disadvantages of this methodology was the difficulty in matching the level of the slab panels to the adjacent structures. So the wharf on one side and the landside abutment on the other, as well as the levels of the neighboring slabs. We didn't want to introduce any steps in between these structures. Obviously, we wanted it to be a smooth surface on top for traffic and machinery to be able to traverse. Unfortunately, due to the length and the age of the structure, we found that bearing shelf where the precast panels were supposed to sit was very not uniform. It meant that the slabs were either moving around or wobbling after they were placed in, or had a step in them, or just didn't quite meet the dimensions that we needed to ensure that the surface was smooth for traffic. Additionally, if the new precast panels weren't sitting uniformly on a uniform bearing surface that introduces a lot of other structural concerns like torsion and bending, which we really did not want to introduce. The solution for us then was to build up that bearing shelf along the length of the slab. This was tailored to account for the lack of uniformity underneath, so it ended up being a nice even surface, providing a place for the panels to sit on. And we were able to further adjust any slight discrepancies in the levels with changing the thickness of rubber bearings just to make sure that they weren't wobbling after they had been placed. Couldn't find any good pictures of the finished product, but this is a nice aerial. You can kind of see that white strip in each individual panel as it sits there nicely. Now the Wharf 5 extension relieving slab. So this is a far smaller relieving slab in terms of length compared to Wharf 1 and 2. It's only 50 meters compared to the 330 meters that we had before. What you see on this aerial there is Wharf 4 and 5 to the left and Wharf 6 on the right. So Wharf 4 and 5 were built together in around 1980. Wharf 6 and 7 came along a little bit later. And when 6 and 7 was built, they ended up bridging the gap between the two wharves with Wharf 5 extension. Similarly to Wharves 1 and 2, this is an asset that Port of Brisbane owns and it's leased to a customer. So we have that customer interface and operational considerations for this project as well. I won't go into much detail or any detail on the whys behind this replacement because it's almost identical to the issues that Brodie explored in great depth for Wharves 1 and 2. As you can see, we had significant cracking, delamination on the underside of the slab. And in this, this is an extract of the condition report that we got done. And as you can see from the extent of the damages, we really had limited options, but to essentially demolish and rebuild. Now, considering how successful the precast methodology was for Wharves 1 and 2, we really wanted to do it again for this one. However, it was quickly determined that wasn't going to be an option, unfortunately. What you see on the right is a graph of the surveyed levels of the abutment and the wharf and their soffits. What it shows is basically significant undulation along the adjacent structures. You can see about halfway around that 25-meter mark, something interesting happens. So the abutment support on one side is actually higher than the wharf. So it starts off in one way, and then over the length of the slab, it actually ends up turning like this. This is a far greater challenge in terms of the levels than we had in Wharf 1 and 2. So it's not something that we could have simply resolved with and building up that bearing shelf or changing the bearing pads that were underneath. So unfortunately for this project, we ended up going with an in situ reconstruction instead of precast, as much as we wanted to. Some of the construction challenges that we faced for Wharf 5 extension, just like Wharves 1 and 2, the previous slab was cut into pieces, placed onto the back of trucks and disposed off-site. You can see a very similar extent of defects that we also observed on Wharves 1 and 2. However, this demolition brought about some pretty unforeseen challenges. As the contractors were cutting the old slab into pieces, that bottom portion of the slab that was delaminating that you saw before ended up falling off. It really was not really holding on. Luckily, the contractor had placed geofab down on the rock wall and it caught most of the debris, but it certainly created a lot of extra mess and cleanup that we weren't expecting. So we ended up having a little bit of extra work ahead of us. In addition to the demolition, as with Wharves 1 and 2, we were again working over water. However, this ended up bringing some further challenges in terms of formwork. We didn't have the luxury where we were just dropping the new slab in place. We actually had to form up so that the concrete was able to be poured in situ. This meant the subcontractors that were in charge of the formwork actually came up with a pretty innovative solution. So they developed a system where they propped up the formwork using a system that was sitting on the bearing shelf, the abutment shelf, sorry, and was secured to the underside of the crane beam on the other side. So this is a little bit of what it looked like. Overall, the slab was completed in 3 pours, and what you're seeing there is the size of the first pour. So it was a pretty significant portion. So much like Wharves 1 and 2, we were in the middle of an operational terminal. You can see just how close we were to that ship behind. Those key cranes that you can see in the background, they had to traverse over our work site sometimes multiple times a day. So operations always came first. There were multiple instances where we had to allow the crane to pass over. We worked in with the terminal operators, allowing them to basically come in, open the fencing if they needed to. We would get everybody off site. The crane would pass over, and then we would resume work very, very quickly. Security was a little bit of a challenge, not from what you'd expect, but all waterside terminals essentially at Port of Brisbane are maritime security zones. Each terminal operator has their own security in place to manage this. DP World have a very strict escort requirement. No one can come in or out of the terminal or move around the terminal unless they're escorted by security from their security staff. Normally, this isn't much of an issue. Yes, you might be waiting around a little bit if you're unlucky enough to get there during like a shift change. I think the longest I've ever had to wait was probably 25, 30 minutes. However, as you can imagine, in a construction site, we have a lot of people coming in and out, coming and going, moving around. And most importantly, when you have concrete trucks coming with our precious concrete, we didn't have time to wait 25 minutes for an escort. So we were able to work in with our customer to provide a dedicated escort on those critical days. But the rest of it, basically the contractors had to really manage their site activities accordingly. Weather. So the mouth of the river at the port brings with it some pretty severe weather conditions, including wind and rain, which we have been experiencing over the last few days. The wind on the days that we were pouring concrete was very challenging. We actually ended up asking DP World if they could spare some containers and basically form a wind barrier around our site. So that was pretty effective in blocking the wind, but again, it's not really something that we had thought about beforehand. It was a very quick solution that we came up with on the day and ended up working quite well. And of course, the last thing you want in the middle of a concrete project is a tropical cyclone. So tropical cyclone Alfred made an appearance, luckily after we had poured the last segment and we were in the curing phase, but we had a lot of work to do to ensure that the site was all secure and the project wasn't going to be compromised by that in any way. A little bit about the concrete. So the concrete mix that we chose was a hybrid alkali activated concrete, which essentially is a low carbon alternative, 50 MPa design strength. 70% of the cement content that a normal port mix that we would have used was actually substituted, which then resulted in around about a 40-ton saving of carbon emissions. This was the first time we actually implemented this concrete out at the port, and from all accounts, it actually was surprisingly easy to work with from the contractor's perspective. Some other project fun facts, 38 tons of steel went into that one. So that's a significant amount of steel, 207 tons of concrete. Took about 4 months overall, which is quite a long time considering the slab was only about 50 meters long, which just goes to show how much efficiency there is to be gained in a precast solution. No operational delays, the customer was happy. Here's a little look at the finished product. As you can see, from substituting out that cement, we ended up with a very bright white concrete, which is visible from space. So yes, this is just like the aerial for 1 and 2. This is what the relieving slab looks like. Key considerations. So really the biggest takeaway from this, I reckon, is you really need to consider the suitability of your construction methods for each project. As you can see, these are very similar projects. They're both relieving slabs, but they were delivered in completely different ways. So we really need to just consider what is most important, if it's cost, if it's time, if it's your quality outcome. Really just consider which methodology works best. Pick experienced contractors with robust QA and safety management systems. This is pretty much a no-brainer. Penzar obviously are fantastic contractors, but it makes a world of a difference when your contractors have that experience in projects where there's so many variables that come up, and timeline is of a critical nature to the project. It goes a long way. A lot of headaches are saved in that regard. Keep the customer happy. So for us, in particular at the port, we are a customer-facing business. These terminal operators, they lease these assets from us. So in order to maintain that relationship, obviously works like this are unavoidable. Sometimes we have bigger upgrades coming as well. So if we don't prioritize the relationship with the customer, then it makes delivering projects like this extremely difficult. But overall, it was really, really lovely working with everybody. We got the job done, and now we have some nice new relieving slabs. And that's it from me. Thank you very much.
Good. Thanks very much, Diane. I'll just take remote control back from you. Great. Good. Thank you again. And ladies and gentlemen, please join with me in thanking Diana for a very interesting and detailed presentation. Right. Okay. I just we'll move to Q&A. The first question which has been asked by Andrew, and he's asked. Well, certainly he's complimenting you, thanking you both for your presentation, and commented that it's great presentations. And this is Andrew Siccardi from Master Builder Solutions. He's interested in your thoughts regarding possible FRP strengthening to assist with crack control or remediation. Perhaps structure was too far gone. And secondly, the role of saline corrosion inhibitors as sealers for the precast solution to assist with design life and durability protection from the future ingress of chloride ions. Now that can be a question to either Brodie or Diana. Anybody like to have a go at that?
I can probably start. Yeah, good question, Andrew, and thanks for a bit of a loaded one there. Yeah, look, FRP as the laminates, the structure was too far gone in this instance. So yeah, as you rightly pointed out there's the opportunity to increase or contribute to the overall capacity through the addition of surf-supplied FRP. Yeah, given the deterioration that we're seeing and the existing corrosion, it'd be like gluing a band-aid to the soffit of the slab. Or as soon as it starts to delaminate, it's not providing any benefit. Certainly, I think, taking a bit of a tangent to it, but for the new installations, like GFRP bars as an inclusion is a possibility, not necessarily something that we contemplated, given the risk-averse nature that the port take around these types of assets, and the potential uncertainty around how they'll perform in that environment. But I think certainly something that we've been keeping an eye on for the future as to whether we could do a combination of different reinforcements for a new installation. On the topic of inhibitors, so I think Diana could probably talk to the mix and the use of corrosion inhibitors in the new mix design.
That's right. So the hybrid alkali activated concrete, the alkali activator part of it was an additive that was put into the mix, and that had multiple uses in this instance. First of all, it was ultimately a corrosion inhibitor, and at the same time, it also helped workability and basically the overall. We think the addition of this particular product was basically that was the corrosion inhibitor.
Yeah, the other part that I would add is for the port standard mix design, we have nitrite corrosion inhibitors added in. So we typically take between 15 and 25 litres per cubic metre of nitrite through all of our reinforced concrete elements in a marine environment. But certainly when it comes to alternative methods we're definitely open to exploring, but in a measured way, as you've seen.
Brodie, I'd also like to ask you a question. You mentioned that the standard design life for the Port of Brisbane is 50 years, and some other infrastructure government departments are thinking along the lines of maybe even extending beyond 50 years, because quite clearly some of our structures, like those ports and harbour and marine installations, will probably be working for longer than 50 years, one would imagine. Is there any thoughts at the moment within the Port of Brisbane to extend initial design life beyond 50?
Yeah, good question. And it certainly is. So for all of our new infrastructure, we've been trying to push well beyond that 50 years. So whilst that's the nominal design life, we've introduced a range of measures to try and considerably increase it. So whilst we haven't quantified to say that it's a 100-year design life or 150 odd year design life, I think all those incremental things that we've done along the way have tried to add to that. So one of the big learnings that we took through the initial 1996 study was around the implications of constructing closer to the water level and to the tidal zone, with most of the assets being close to around 0.5 metre to 1 metre maximum from the water level or from the high tide mark. They're consistently being exposed to that splash and spray environment and replenishing chlorides right at the surface of the slab. Through that time, we've incrementally increased the height of all of our wharf assets. So the newer wharves are at least 2 metres higher than the older wharves. That's one feature that we've included. We've increased the cover to the reinforcement to try and address it. We've tightened up crack widths as part of it, and as I say, we've introduced corrosion inhibitors into the mixed design. So again, it's difficult to evaluate the combined outputs of that, but yeah, we certainly are trying to push well beyond that 50-year design life, but providing things like reinforcement continuity as standard to make sure that we have the option of doing CP as a treatment at the time of corrosion initiation to make sure that we're going well into that second or third life.
Right. Diana, a question for you too. In the reconstruction of Wharf 1 and 2, you use a precast solution for that. How far away was the precast yard, roughly? Because I imagine you had some fairly big and heavy slabs to transport there. Was that a major logistical issue?
Brodie's probably better off answering that one.
Yeah.
I actually don't know, sorry.
Yeah, good question, John. It was so I can't remember the exact location, but within an hour's distance from the Port of Brisbane. Interestingly, that was probably one of the key challenges that we had, being in that COVID environment, trying to get infrastructure built when everyone's chasing it at the same time, and trying to find a precast that would be able to support us. So we're fortunate in our relationship with the precaster to be able to get them to prioritise our assets. But yeah, it definitely was one of the key considerations at the time, and definitely something we contemplated whether we switched to cast in situ, given that the entire industry was busy at the same time.
Okay. A question for the Wharf 5 and 6, or perhaps the Wharf 5 extension. And Diana, you mentioned that high wind was an issue, which you had taken precaution of windbreaks, and also, of course, high temperature, which you'll get in Brisbane. And of course, those two conditions are diabolical for concrete placing. And the question is, did you get much plastic cracking as a consequence of the high temperatures and the high winds?
The very first pour we did, yes, when we did experience that much wind, obviously we timed the pour to be first thing in the morning, so just as the sun was coming up. That was then a lesson that we carried on to the subsequent pours. We were a little bit quicker with our curing process, so just even as much as a 20-minute delay between when you finish working the concrete and when you put the curing onto it, that can make a big difference. So yes, I hope that answers your question.
Right, okay. Now, here's an interesting question too. It's not a trick question, but I noticed your comment too about the importance of picking experienced contractors, and I think everybody universally would agree with that. It's absolutely fundamental. But how much is that taken into account and weighting is given to it in the assessment of successful contractor? For example, against the criteria of price. An interesting question because that often becomes very difficult issue to
It
solve,
is.
especially when you have budgetary issues that you have to answer to. Yeah.
Correct. I think the answer to that is going to be, it depends. Based on essentially the criticality of the project. So it can change, we can change the weightings depending on the outcome that we're trying to achieve. I can't really speak to Wharf 1 and 2, but for Wharf 5 extension, I mean, I should mention that it was actually done by the same contractor. So the fact that they had delivered Wharf 1 and 2, hence I already had that experience in place. So we did end up going to tender again, but because they had that experience, especially directly relevant to the port, that was one thing that was a big consideration for us. But in general, for projects that I deliver, I definitely value experience almost as important as price. Budgets are budgets, but in terms of quality outcome and the longer term durability of the asset, that experience portion of it is, you can't understate the importance of it, especially because in our operational environment, things can change at the drop of a hat. You have a contractor that has either never worked in an operational environment like that. Some of them actually genuinely don't know how to deal with any of these issues that come up. So for us, it does go a long way. And as a customer-facing business, I will say that sometimes we are willing to pay a little bit more just to make sure that our customers are looked after and also we get a better outcome for the asset.
Brodie, just a question too. You mentioned that for slabs 1 and 2, or for wharfs 1 and 2, the cover, was 60 to 75 millimetres, which, to be honest with you, a lot of people would say, yeah, that's the expected cover you'd have for that sort of structure in that exposure condition. So the question is, well, is 75 millimetres in that circumstance inadequate? The issue of cover, is there a case to say that maybe cover should be greater than 75 millimetres? And then, of course, we get involved, well, then you have this layer of unreinforced plain concrete on the outside of the concrete. How does that manage cracking? So it's a complex equation. What thoughts would you have on that?
Yeah, great question, and something we certainly contemplated throughout this process. We're fortunate in the fact that there are quite significant covers, as you say, from structures that were designed well before contemporary standards. So in terms of the initial question, I think the new design that we put in was only 75 mil cover, and it took the view that, well, the cover is significant in the uncracked sections where we're performing quite well, and particularly when we start talking about adding in all these other treatments to the reinstated slabs, we'd expect that it should be able to achieve it. So I think the question, as you pointed out, really came down to how do we control cracking to minimise the potential for it to occur and for us to create these secondary issues with chlorides being able to ingress and moisture being able to ingress directly towards the bar. So yeah, as I say, we tried to restrain cracking as best we can, adding in additional reinforcement to take it out. But yeah, as soon as you start pushing more cover, induces greater crack widths, and yeah, the equation is a bit circular in that respect. So it is a delicate balance and something that we've tried to toe the line on quite finely.
A question too about the 90-ton axle loads, which are savage beasts, of course, as far as equipment goes. And while in both of those jobs you were restricted by levels, and so really the replacement option that you had, you were constrained by those issues. But if you were in a greenfield situation and you were designing a slab where you didn't have restrictions on geometry, how would you approach the problem? Would you perhaps be going down the path of designing for a greater allowable working stress, especially for the 90-ton monsters?
Yeah, I think we would, and that's certainly how our approach has panned out more recently. So we've tried to accommodate for significantly higher stresses, accepting that even if it doesn't happen now, it's going to be in the future. In the same way that back in the 80s, no one even contemplated that you'd have such heavily loaded boxes. So I think whilst it's probably not a necessity now, it will be in the future, but equally putting putting far more reinforcement and accommodating for higher loads will reduce the stress at the bar. So yeah, definitely a benefit if we can do that. And as you say, if we had a greenfield site, and we certainly do into the future for newer wharves, that's definitely how we'd approach it.
Okay. Well, one last question, which has been asked from the audience, and that is, what was the time frame that it took for the precast yard to complete the slab? And what was the age of the precast slabs at the time of placement? And then another question, of what age of the structure do you intend to complete the future inspections?
Yeah, I'd say my memory's a bit hazy on this one, but so we didn't place them before 28 days from my memory, but yeah, it's sat in the yard for most of that duration, and we completed them in batches, so it would have been I think it was 6 or 8 panels at a time that were cast by the precast yard, which worked in with how we staged our construction. So we take out a section plus a little bit to provide some working space between the old and new, then demolished, dropped in new slabs, and then repeated that process. So just by having that, it was probably about a 6-week cycle from memory, enabled the precast yard to stay ahead of us to be able to continue to work in front of them.
Right. Okay.
But yeah, in terms of future inspections, I think we've, even for the newer assets that we add on, we add them into our overall inspection and testing regime. So they get added into our annual maintenance inspections, added into the 5-yearly condition investigations and assessments that we do.
Okay. All right, ladies and gentlemen, I ask you to thank both of our speakers, Brodie and Diana, for two, in fact, very great presentations.